Now we're going to examine relationships between numerical variables or continuous variables. Now, some examples of this are things like as disposable income increases nationally, our retail sales may increase, or as obesity rates increase globally, life expectancy drops, or as temperature increases globally, sea levels may increase. So when we're looking at the relationships between continuous variables, we're looking for the tendency of variables to move either in the same direction or in opposite direction. And we have two methods that we'll primarily use for this. Number one is we'll use a graphical method using scatter plots and trend lines, and statistically we can actually calculate numerical measures to give us a better idea of what's actually happening. And sometimes that's important because you may or may not be able to see some of the trends easily in a graph, although most times you will. So let's take an example. To the right, we have a data set, a subset of data actually, containing two variables. The duration of an eruption of the Old Faithful geyser in Yellowstone National Park, as well as the waiting time between eruptions, or between that particular eruption. The full data set contains about 272 data points and measures what we had said, the waiting time and the eruption duration. Now, an analyst might think, looking at the numbers, that there might be a relationship between the two variables. And it kind of seems, looking at this just by eyeball, that when waiting time is longer, the eruptions might be longer. Since they're both numerical, we can easily take a look at this, and we'll use a scatter plot to take a graphical examination. Here we see a scatter plot, and we can clearly see along the x-axis the eruption duration, and we could see the waiting time associated with it. This chart is produced in Excel, and there is a way to produce the trend line, which is that red dashed line, and we can definitely see an upward trend. By looking at this, we can also tell that it's a pretty steep incline. It's not a weak incline, so we can say that there seems to be this stronger relationship. And remember that the scatter plots are using an XY coordinate scale, which are Cartesian coordinates, and they will tell us how each one of these points are associated with how each point on the x-axis is related to a point on the y-axis. And we could use it for prediction. So for example, we might be able to say that as we look on the x-axis, that if the waiting time, let's say, is 90 minutes or 90 seconds, the eruption duration will be about 5 minutes. So there are two statistical ways that we can actually take a look at this. We can look at something called the covariance and the correlation. Now, it's important to remember that prior we had two other measures. We had a variance and we had a standard deviation. And there's a similarity to this. In the case of the variance, we were looking at how much a single variable was dispersed around the mean. Well, in the covariance, we're actually looking to see how two variables are dispersed around their means together, and looking for a relationship between the two. And therefore, the covariance measures how much the movement in one variable predicts the movement in a corresponding variable. Now, correlation standardizes the covariance and makes it scale invariant. And what we mean by that is we compare two variables with different scales. So if you have a covariance on the same scale, then you can actually interpret the actual value a little bit better than if you could where you had two variables with different scales. For example, two variables measuring, say, IQ and miles per gallon. You can't relate the two. You can get a covariance number, but are you doing it in IQ score or are you doing it in miles per gallon? It kind of doesn't make sense. However, correlation will allow you to interpret it quite easily. So in the covariance, we're measuring how much the movement in one variable predicts the movement in a corresponding variable. Now, to calculate a covariance, we need to measure how each observation in one x differs from its mean, which we call x bar, and see how the corresponding observation of the other variable, y, differs from its mean, which is called y bar. And so this is important to understand how much change is occurring in both around their mean and the direction of that change. So what we do is we have our calculation as such. We're going to basically add up all of these differences, xi minus x bar times yi minus y bar. We add all those up and then we divide by n minus 1. If you remember from our variance formula, this was very similar to taking the average difference between the two. Now, we don't really need to do the entire calculation because Excel does this for us. we can actually calculate the covariance using the covar function, where we have our data set 1 and data set 2, which would be synonymous to an X data set and a Y data set. Now, correlation will standardize the covariance, and it makes it what's called scale invariant, which allows us to compare two variables with different scales. Again, two different scales would be something like an IQ measurement and miles per gallon. They are on two totally different scales. So if we do have two variables such as grade score and the height of students, we'll have two variables that are on different scales. Using the covariance is difficult to interpret. Correlation is represented by the Greek letter rho, which looks like that little p, and it is much more widely used in interpretation. And that's because of this scale invariance, and we've heard this notion of two variables being correlated, and this is where it comes from. So this making it scale invariant is what happens when we standardize a metric. And standardizing a metric is really going to have to do with dividing it by its standard deviation. Since we have two variables that we're working with, we're actually going to be dividing it by two standard deviations, the standard deviation of x and the standard deviation of y. And that's what's represented here in the formula. So we have our rho, which is our correlation. We'll sometimes represent it as COR, x and y variables, so the correlation between x and y. And it is basically a fraction. The covariance of xy divided by the standard deviation of x times the standard deviation of y. And the more mathematical formula, which you can take a look at more closely, is on the further right. However, in Excel, once again, we don't need to do the formula. We don't need to have all the mathematics behind it because it does it for us using the Correl function, C-O-R-R-E-L, data 1 and data 2 to obtain the correlation value. So what do the values of covariance and correlation look like? Well, let's go back to the example that we had before with eruption duration and waiting time. Covariance values can be any number that's negative or positive. And correlations, however, are standardized and will be a number from -1 to +1. Negative correlations are less than 0, mean that two variables are negatively correlated. That means they move in opposite directions. As x goes up, y goes down. Or as y goes up, x goes down. Positive correlations are correlations that are greater than 0, and it means that the two variables are positively correlated. They move in the same direction. As x goes up, y goes up, and the reverse. Now, correlations that are close to 0 mean that there's no correlation between the two variables, and therefore we would consider those two variables independent of each other. There's no dependency one way or the other. So let's look at the example again. We have our data set on the right, and what we're going to do is we're going to calculate the covariance and the correlation. So we'll end up with a number here for the covariance, again, A2 to A273, B2 to B273, and the result is 13.93. Now again, that 13.93, since these are both in minutes, it's a little bit easier to say, the covariance is roughly 13 minutes. However, if we had two different scales, we wouldn't be able to say that. But it's not as easily interpretable as the correlation, because here we have our correlation, again, using the same two columns, and our result is 0.90. So it's clear that it's on the positive scale, and we know it will only go up to 1, and this is really, really close to 1. So therefore, it is a very strong correlation, a very strong positive correlation, and that's pretty much evident by the scatter plot that we've posted here as well. Now, looking at a couple of different types of correlations here, or at least values, we should say, we have anything that's forming a straight line would have a perfectly positive correlation, and that's this chart number 1 in the upper left. So if it's a perfect straight line, you're going to see the correlation of 1.0. Now, if it's a perfect straight line going downward from left to right, then it will be a correlation of -1, and that's a perfectly negative correlation. Now, if we look at the bottom two on the left, you're going to see a scatter plot of dots that seem to generally move up, but it's not a perfect line. And in this case, this correlation was calculated at 0.89. This is a positive correlation. It's a linear correlation and will show an increasing trend. Right next to it, we have a negative correlation of negative 0.74, and you could see the scatter plots generally moving downward, and that's our negative linear trend. Now, the two items on the right at the top, we have kind of like a scattering of items. Almost it looks random, and the correlation was calculated at 0.04. and that's close to 0. So there's no obvious pattern shown in that chart. But sometimes we'll also get a correlation, in this case down below, a negative 0.09, which is also close to 0. It doesn't have that cloud pattern, and it's obviously that there is a pattern that you could see. It's this inverted U. But in this case, this is not a linear trend. This is actually a curved linear trend. And therefore, the correlation says that there is no correlation, and we'd have to do some other things with this because there turns out there is a relationship in this case, but it's not linear, so correlations won't be able to pick it up. Now, here are some guidelines when you're using the correlation. So we do have some statistical tests that can determine the strength of correlation relationships, but here we're just going to provide some guidelines. So number one, the more data points you have, the more accurate these guidelines are going to be. So for example, if you only have 8 data points and you find that the correlation is 0.4, you may add another 8 data points and find that that correlation drops from 0.4 down to close to 0. So it's important to have enough data points. Now the second part is there's no magic number of data points. Generally, you'll see some books refer to, well, you should have 30 or you should have 50 and so forth. And there are some statistical techniques to say what is the number of data points that you're actually going to need. But let's just say that it should suffice that if you have somewhere between 30 and 50 of these variables or more, observations or more, that you'll have enough to determine a good general correlation. The analyst should determine if the data itself is sufficient to make a conclusion. But what will happen is that as we add more data, we do additional tests, such as effect size, power, and understanding the normality of data. Is it truly linear? Is it not truly linear? Some of those things will change our outcome, but this is for more advanced techniques. So if you believe you have enough data and you have a linear trend of data between X and Y, then what we can basically say is we can use these two tables here to determine whether it's a very strong, moderate, weak, or 0 or no correlation at all, both on the negative side and positive side. So things from the 0.8 to the 1 are going to be very strong. Things from 0.6 to 0.8 will be strong. Things from negative 0.4 to 0.6 will be moderate, and 0.2 to 0.4 will be considered weak. So anything below 0.2, so between 0.2 and 0, and negative 0.2 is just going to be considered no correlation.